Hi there. I'm going to teach you about Monte Carlo sampling. So Monte Carlo sampling is a technique for drawing characteristic samples from probability distribution, and it's typically used in cases where the probability distribution is in some way difficult to work with, either because it's extremely high dimensional, or because it can't be analytically normalized, or because it's complex in some other way. Monte Carlo sampling is a fundamental concept in basically any field that works with large amounts of data. It's used in physics for designing nuclear weapons. It's used in biology for modeling the way proteins fold. It's used to model the weather. At Khan Academy, we even use it to power our adaptive testing. In Monte Carlo sampling, as in any kind of sampling, you start off by defining a target distribution, which you wish to draw characteristic samples from. So I'm going to call the target distribution P of x, defined as P of x is a probability distribution, so it has to satisfy the usual properties. Probability has to integrate to 1, and probabilities can only be greater than or equal to 0. As an example, let me sketch a probability distribution P of x in 2 dimensions. So here our state space is x, and x is a 2-dimensional real number, so we say that x is in part of the 2. And now I'm going to sketch an example probability distribution. So I'm going to do this by sketching isocontours. This inner isocontour shows the edge of the most probable region, and maybe this region, or maybe this contour has a probability density of 2. Note that because P of x is a probability density function, it's okay for P of x to be larger than 1 as long as it is larger than 1 only for a small region, so for a region that is less than unit area. And so now let me draw the next iso probability contour, and maybe this is P of x is equal to 1, and we'll do one more out here. So maybe this is P of x is equal to 1/2. So in sampling, we want to draw characteristic samples x from P of x. So for instance, for our probability distribution to the right here, we would draw a large number of samples from this central denser region, and we would have fewer samples, so a lower density of samples in the less probable regions. What Markov Chain Monte Carlo tells you how to do is how to actually generate these samples. So in Markov Chain Monte Carlo, the next sample is drawn based on the location of the current sample. So MCMC, or Markov Chain Monte Carlo, is defined by a transition distribution, which tells you how to draw the next sample based upon the current sample. So we're going to call that transition distribution T of x prime given x, defined as, and what this gives you is a probability distribution over your next sample x prime, given that your current sample is x. So since it's a probability distribution, it has the usual properties in that it integrates out to 1, and in that it's non-negative. So practically, the way that works is if you start off with a sample at some initial location x, then you draw your next sample from the distribution T of x prime given x. So usually this will be in the spatial neighborhood of x. So maybe you start off with a sample here, and then you draw a new sample from the conditional distribution over x prime given x, and you end up with a sample from here. And now you start at this sample, and you draw a new sample from the conditional distribution given by t conditioned on this sample, and maybe you end up here. And you continue in this fashion until your sampling chain, or your Monte Carlo chain, has explored the entire probability distribution. The time it takes for a Markov chain to explore the entire probability distribution is called the mixing time. And for complex probability distributions, the mixing time can in fact be extremely long. And a lot of research in sampling concerns ways to design these conditional distributions, t of x prime given x, such that the mixing time for the sampler becomes as short as possible. That tells you the mechanics for how to update your samples, but now we need to figure out how to design t such that it draws samples from the correct distribution, from our target distribution, p of x. In order for t to draw samples from the target distribution, the target distribution needs to be a fixed point of t of x prime given x, or it needs to be an equilibrium distribution for t of x prime given x. What that means is if you start out with a whole bunch of samples which come from p of x and you update all of them using t of x prime given x, then the resulting samples still need to come from the correct probability distribution, p of x. We can write out this requirement explicitly as a fixed point equation for the sampler. The fixed point equation says that if you start out in the target distribution, p of x, and you apply the transition distribution, t of x prime given x, then you will still be in the target distribution. In addition to the fixed point equation, the transition distribution, t of x prime given x, must satisfy one other requirement, which is known as mixing. And what this requirement says is that it must be possible by repeatedly applying t of x prime given x to get from any initial location in the probability distribution to any other location in the probability distribution. For most of the choices for t of x prime given x that you're likely to make, mixing will automatically hold. I'm not going to go into the details of this in this current lesson, but the mixing constraint is usually stated more precisely as a constraint on the eigenvectors and eigenvalues of the transition distribution T. To summarize, I've given you an introduction to Markov Chain Monte Carlo sampling. I've taught you how to generate samples by repeatedly drawing new samples based upon the location of the current samples via a transition distribution, t of x prime given x. And I've given the constraints that t must follow in order to draw samples from the target probability distribution.